Edexcel Core Pure, second order differential equations, the homogeneous case. Auxiliary equation with imaginary roots. Just recapping what we've seen in previous videos, if we look at a second order linear homogeneous equation, so we've got 0 on the right hand side, we know that this will always generate an auxiliary equation of the form am squared plus bm plus c equals 0, and we've previously seen that if this auxiliary equation has a positive discriminant, then we'll have y equals a to the lambda 1x plus b e to the lambda 2x. If the discriminant is 0, then the auxiliary equation has a repeated real root and we get the general solution y equals a plus bx e to the lambda x. But what we're going to consider now is what would happen if the discriminant was negative. So here we've got a d2y by dx squared plus cy equals 0, and we could try y equals a e to the mx. If we differentiated that twice and subbed everything into the differential equation, we'd end up with our auxiliary equation, which would be a m squared plus c equals 0. And if we rearrange this, we get m squared is minus c over a, and we can see that we're going to get all plus or minus beta I. So we have imaginary roots this time, and they're imaginary because the auxiliary equation had a negative discriminant, and that means that my general solution could have the form y equals a e to the beta I x plus b e to the minus beta I x. And it can be shown that that general solution can be expressed as y equals a different constant p cos beta x plus q sine beta x, where p and q are different arbitrary constants from the a and the b. And in a moment we're going to look at how this can be changed into this new form. So looking at this general scenario, we created our auxiliary equation, am squared plus c equals 0. It had two imaginary roots, which are called plus or minus beta I, which created the general solution in this form. However, we can show that this is exactly equivalent to y equals p cos beta x plus q sine beta x, where p and q are new arbitrary constants. They're not the same as the a and the b. So just to have a look at how we got from this general solution to the alternative general solution, we have seen that e to the I theta can be written as cos theta plus I sine theta, and e to the minus I theta can be written as cos theta minus I sine theta. Using these two definitions, we can rewrite y as a, so e to the beta xi would become cos beta x plus I sine beta x plus b, and e to the minus beta xi would become cos beta x minus I sine beta x. Now if we collect like terms, we'll see that there's a plus b is the coefficient of cos beta x, and that I a minus b would be the coefficient of sine beta x. So now I can redefine a plus b as p and I times a minus b as q, which gives me the general solution of y equals p cos beta x plus q sine beta x. So this is the general solution if you have imaginary roots. It's worth saying, although it's good for you to understand why this general solution is in a trigonometric form, you don't need to reproduce all of this in a solution. So most solutions you wouldn't really mention that step or this explanation either. You could go straight from m equals plus or minus beta I. You can go straight from that to this new general solution without having to explain the process involved. So here we have an example. We're going to find the general solution to d2y by dx squared plus 36y equals 0. So here we're trying y equals a e to the mx, and that will lead to an auxiliary equation of the form m squared plus 36 is 0, and therefore m is plus or minus 6i. As soon as you see that you've got an imaginary pair of roots or values for m, then you can go straight to the general solution in the form y equals p cos 6x plus q sine 6x. So notice the general solution has a trigonometric form. Notice it doesn't contain any complex numbers or I. You do not need I anywhere in this version of the general solution. So we're trying y equals a e to the mx, and we've written down, as we always do, our auxiliary equation. Its discriminant would be negative, and we get m is plus or minus 6i, and therefore the general solution is y equals p cos 6x plus q sine 6x. And we can have a look at this general solution in a little bit more detail on a GeoGebra file. So at the moment I've set p equal to 1 and q equal to 0, so we're looking at the solution y equals 1 cos 6x. Notice, if keeping q as 0, if I change p, then I'm changing the amplitude of this cosine wave, which is symmetrical in the y-axis. If I set q equal to 1 and p equal to 0, which is there. Now we're looking at the solution y equals sine 6x, which is a sine wave with amplitude 1, and by changing q I can change the amplitude of this sine wave. What becomes more interesting, and you will study some of these features in core maths, is if I start changing p and q. If I start changing p and q, I can change the amplitude of the wave, but if you look closely, I'm also changing the what's called the phase shift of this wave. So it's not symmetrical about the y-axis, and it's not going through the origin. We can make this curve move around and change its amplitude depending on p and q. So if I finish off with p is 1, q is 1, that's what the solution would look like. That's y equals cos 6x plus sine 6x. So in the next video we're going to be looking at auxiliary equation with complex roots.